Now let us start our discussion to understand these topics, these questions. In the last lecture, we had discussed one method of harmonic oscillator solution, the quantum mechanical harmonic oscillator analysis, and that was the algebraic method. In that method, we came to know about the two operators, the raising operator and the lowering operator, the A plus and A minus. They are also called creation and annihilation operator, and they have specific meaning. When we discuss the other topics, it will become more appealing to you. So in the quantum mechanical analysis of harmonic oscillator, the other method is the analytic method, which I should say frankly appears a bit tedious, bit difficult to the student, because it introduces you to some new mathematical tools, and whenever mathematical complexity is increasing, it becomes irritating. This is a fact you cannot deny. But unfortunately, we cannot skip this portion, this mathematical analysis. But I will try my best, I will give my best efforts to explain the things in the most simple manner possible. And once you understand the magic of these mathematical operators, you will enjoy it. And if you have some difficulty, you are always welcome to suggest your opinions in the comment section. So let us start. So what we do in the quantum mechanical analysis with any situation, with any potential, we write the Schrodinger equation. This equation number 1 is the Schrodinger equation. This is well known to you. Now this equation, what we will do, we will make it more neat and clean. We will make it more simple, look simple, so that it is approachable to us. So what we have to do, we have to get rid of these constants, or we have to manage these constants in some manner, so that the equation looks familiar to you, a familiar differential equation or something like that. So what we do, we make a substitution. Chi is equal to m omega by h bar x. This is a substitution that we have made, and this chi is dependent on x because other things are constant. Omega is root under k by m, k, h bar all are constant, so chi depends on x only. And here I have done some rough work to explain you what is this chi, or how to relate this. Well, I will come to this point later if it is required. I don't want to increase any complexity. So with this substitution, our equation 1, the Schrodinger equation, it gets a clean, neat and clean look. And this is our equation number 3. This is much simpler. It looks much simpler than this equation number 1. You can see this. Now this equation, which is familiar to us, or at least which looks familiar to us, we have to solve this equation. This is the differential equation, you can see. Now you have to remember, you noted down that chi is root under m omega times x. X is out of the root over, and k is the energy. K is the energy that we have considered in the last section, half h bar omega, and this is a very significant topic of quantum mechanics. I am explaining how it is. So this k, you can write it as 2e by h bar omega. You can write this. So our equation is reduced to equation number 3. Now what we have done here, in the right hand side, we have this quantity k which depends on x, and we have this quantity k which is energy. Now what we have to see, just to try to understand the physics behind the equations, then things become more interesting. Whenever we have a minus sign, we are actually comparing chi and k. We are comparing chi with K. K is energy, and chi is related to something which is depending on x. What is x? X is the displacement from the mean position. X is displacement from mean position, or you can say the amplitude. You have to keep these things in mind, the physical meaning of these symbols or terms. Then things becomes more understandable, more appreciable to you. X is displacement or amplitude. So what you are doing, what we are doing here in this equation, we are comparing the effect of chi square and k square, means what will happen at large distances, at large x, how the equation will change, how the solution, how the situations will change. This is what we need to do, this is what we are intending to do. So this is the meaning of equation number 3. Now what we need to see, that what happens at large x. This large x, large displacement, large position is a very fundamental thing in quantum mechanics, because you know the wave functions must be finite. They should be equal to 0 at large distances, at large x. So if x is very large, amplitude is very large, amplitude is large, what happens? In equation number 3, chi square will dominate over k square. This is simple mathematics. That chi, if it is very large, x is very large, so chi is very large, chi square will dominate over k square and k square will become negligible. In that situation, our equation becomes still more simple, and it takes the equation form of the equation number 4. Now you can check from your knowledge of differential equations that the solution of equation number 4 is of something this kind. So what is special about 5? It is an exponential equation. And from here you can see that the quantity b should be 0, because at large x, positive x, if x goes to infinity, so chi will go to infinity and this term will blow up, and your psi, the wave function, will also blow up, which is not required. So what we need to do, we have to make this constant 0. So our solution is now much simpler. It is only in the form of a. Now this a has to be determined, or we have to find this constant. This is the tricky part, or this is the so-called difficult part that appears to the student when he is solving the quantum mechanical harmonic oscillator in quantum mechanics. Now this term has to be taken care of, because the wave function have to obey the condition that psi should not blow at infinity. Psi chi, since we are expressing x as chi, should not blow up at x equal to infinity. So a has to be taken care for. A means the constants. A has to be taken care of. Now we need some mathematical tools, and I am telling you frankly that I follow the book by Griffiths. You have to understand this, and he has written in a very lucid language. He says that this exponential has to be peeled off. Peeling means you have to remove the cover, like peeling an onion. So what we have, we don't know what is the form of the constant with this exponential part, and this exponential part is disturbing. Disturbing means at x negative it will again blow up, at minus infinity it will blow up, again the condition is violated. So what we have to do, what we require? So what is required, that this constant or the empty space in the bracket has to be empty space in the bracket, or the constant has to be expressed in terms of chi. It should be expressed in terms of chi. Now, in the most crude manner, I will say that we have to choose the constant, or we have to fill the empty bracket with some terms, so that this problem of blowing up out at infinity is resolved. Means we need something that chi is minus chi square by 2, e to the power minus chi square by 2. It should go to 0 at x equal to minus infinity. Then our problem will be solved. So this is our intention. In order to do this, in order to fulfill this objective, so we express A as h psi, is some function of psi. Sorry, chi, it is chi. I'm sorry, it is chi. Some function of chi. Now, what type of function is required? Type of function is required. This is the problem here. The student finds it difficult that from where these new mathematical terms are coming up. So let me tell you a very important point, that quantum mechanical oscillator, as I asked in the first question, quantum mechanical oscillator is a system where quantum mechanical oscillator is significant. The first question I am answering here, significant because I am writing in this in short form, because it is a system a minimum potential energy, This feature is not found in other systems. You consider the infinite square wave, you find the potential barrier or step. There is no concept of infinite potential energy. Minimum potential energy. The graph is parabolic. This is the point of minimum potential energy, and from this is the mean position. If you are drawing a pendulum like this is the amplitude, and this position is the mean position, the minimum potential energy, and you have to check the solution, you have to check the variation about this minimum as this bob of the pendulum or the block attached with the spring is moving to distance x, the amplitude. This is what we have to do. This is the significance of quantum mechanical oscillator. So what we have to do now, I am telling you how we have to find this constant. We need a constant. That is a series expansion in chi, and remember chi is x. So you have to see the variation of the potential energy and the variation of the Schrodinger equation and the variation of the wave functions as you are moving away from the minimum value of potential energy, minimum value of energy. We need to see a variation of, sorry, this is more appropriate to write E is equal to 0, variation of the wave functions as we move away from E is equal to 0 or E is equal to minimum point. Let me write this E is equal to minimum, it is not 0. And this is the most significant part of this analysis. E is equal to 0. E is equal to minimum. are moving from E is equal to minimum, how the things are varying? This can be understood by a Taylor expansion or a series expansion. So, what we do? We have put h psi as equal to A, and our psi chi is equal to h chi e to the power minus chi square by 2. This is our equation number 6. We don't know what is this h chi. Now we are going to determine it. This is the physics. This is the thing that we are going to do. Now if you differentiate d psi by d chi, because in the Schrodinger equation we need the double derivative, what you get? dh upon d chi, it is a function of chi, minus chi h e to the power minus chi square by 2, and d2 psi by d chi square is double derivative is d2h upon d chi square minus 2 chi dh upon d chi plus chi square minus 1 into h e to the power minus chi square by 2. This is what you are going to obtain. You can differentiate it and you can check. It is not a difficult thing. It is simple differentiation. You know differentiation. Now this h chi, since this is an expansion, h chi is an expansion, or more appropriately series expansion in chi. So the form of this h chi will be a form of expansion. It will contain a term with chi is equal to 0 power, then it will have chi with 1 power, then it will have chi with 2 power, and it will go on. So we can write it from j is equal to 0 to infinity, aj chi j. Remember, chi is a function of x. Now what is happening here in this equation number 7, that we are expressing this constant as a series expansion of x, series expansion of x, which is chi. We want to see how the solution, how the wave function will vary as we go away from the position of minimum energy. Now if you differentiate 7 with respect to chi dh upon d chi, what you will get? A naught will be removed, 0, a1 plus 2, a2 and so on, and it can be written as j is equal to 0, j times aj chi j minus 1. Now the second derivative, how it will look? It is also simple. It is simple derivation, differentiation, so it is not an issue. d chi square, now a1 will vanish and you will be left with a2, and sorry, it is 2 chi is missing here, just a minute. So you will be left with 2a2 and so on, and this will be in the expansion from j is equal to 0 to infinity, j into j plus 1 into j plus 2 aj plus 2 chi j. This is equation number 9. There are so many equations I can understand, but try to concentrate and understand the things. Things are not difficult at all. These are simple derivations, simple differentiations. Now this is what we are going to get by when we are differentiating this. Now what we require, that if you are putting these first derivatives and second derivatives in the Schrodinger equation in terms of chi, putting 8 and 9 in d2h by d chi square minus 2 chi dH by d chi plus minus 1 is equal to 0. This is the Schrodinger equation in terms of chi. You can check this. Now, if you are putting these things, the equation number 8 and 9 in equation number 10, what is required that the coefficients must be 0. So, what is required here? I am taking the things in a most simple manner. J plus 1, J plus 2, AJ plus 2 minus 2J AJ plus K minus 1 times chi to the power j is equal to 0. So what is required now? This thing should be equal to 0. Now, if you are putting this thing equal to 0, then what will happen? You will find that aj plus 2 equate this thing, total this thing to 0. What you get is 2j plus k minus 1 aj by j plus 2, this thing j plus 1 is aj plus 2. This is called, this has a specific name in the language of mathematics, and this is called recursion formula. Recursion formula. It is reoccurring from this equation in the, it is a concept of series solution of differential equations. You can find the different coefficients, and remember our job is to find the different coefficients. This is the recursion formula. Now for j is equal to 0, you can find a2 2j plus, sorry, it will be 0. It will be 0. Let me write it again. It will be k minus 1 a 0 by 2 into 1. Similarly, you can put j, if it is j is equal to 0, you can put j is equal to 2, you can put j is equal to 4. You can find the even coefficients. In the similar manner, you can find the coefficients, odd coefficients. So the even coefficients are built up on a0. This means, now this is a very important point. This means all the even coefficients that are describing your wave function, they are a superposition of the coefficients, or they are the superposition of the quantities based on a0. Similarly, the odd coefficients a1, a3, a5 are built on a1. So this quantity h psi that we assume, it is a sum of h psi even and h psi odd. It is a superposition, it is a summation of even and odd constants. This is the significant part. This is the significant part of this solution. This recursion formula is very important. So what you get, you are getting h psi as a sum of even and odd coefficients. But there is a but. All are not acceptable. Are not acceptable. Because the wave function that should be normalizable. If j is very large, then what happens? a term aj for very large j, it is something like this: j by 2 factorial. It will vanish if j is very large. Or you can say aj plus 2, more it may, let me make the thing simple, is 2 by j times aj. All solutions are not acceptable because for very large j, your normalization will not be possible. Your normalization will not be, you cannot normalize the things, and that will violate, that means everything is in waste. So basically our h psi, I am taking the things very simple, this h psi is something, some constant c times e to the power chi square. This is the solution. This is the general solution of this equation. This is for h psi, not the wave function. Remember, this is not the wave function, this is h psi. And what is our psi? Our psi is something like this: h psi e to the power minus chi square by 2. So you have obtained a plus chi square, so that this can be cancelled out. So if you put x minus infinity, it will go to 0, but still the things are not totally up to the mark. If h is behaving like exponent chi square, then it is extremely essential that the power series has to terminate somewhere. If h chi is exponent chi square, then the series has to terminate. It has to stop. Has to terminate. Terminate means stop. Means it should be 0 somewhere. Otherwise it will not be normalizable. Your wave function will not be normalizable. Otherwise psi chi will not be normalizable, and all our efforts will go to 0, will not be normalizable. So this is an essential condition, that for some j, and for your convenience, for some j, we consider this as n, because the results are expressed in terms of numbers n. Denote j by n. Denote j by n. For some j or some n is equal to n, the series must be 0. Must be 0. Now, how can this happen? This is very easy to see. You see this equation: 2j plus k minus 1 is 0, means 2j is equal to 1 minus k. So this j will be something like that, 1 minus k by 2. And k is energy. K is energy. So if j is equal to 2j plus 1 minus k is 0, then k is equal to, you can find it, because we are interested in energy, or you can say k is equal to 2n plus 1. Sorry, it is, there is a small mistake. Sorry. It is 2j plus 1 minus k. Sorry. 2j plus 1 minus k, and k is equal to 2j plus 1, or if you replace j by n, it is 2n plus 1. So this k is equal to 2n plus 1, and k is your energy. K is your energy. So what important result we get? What is the difference between classical and quantum case? The classical and quantum case, the difference is our energy En is now n plus 1 by 2 h bar omega. This is the energy equation for simple harmonic oscillator in quantum mechanics. And the most significant thing, how it differs from the classical case. If you put n equal to 0, E is equal to 1 by 2 h bar omega, means for n equal to 0, E is not equal to 0. If you are defining n as quantum numbers, there is a lowest quantum number n equal to 0, which is not possible in particle in a box or in finite square well. But here n can be 0. And for n equal to 0 E is 1 by 2 h bar omega. So at the minimum energy, we know that in the case of minimum energy, the total energy is 0. The total energy is not 0. So a quantum mechanical system is said to be quite alive, means it has life even at the 0 state. So quantum mechanical simple harmonic oscillator is alive. Alive means that has life at lowest state, if you are denoting the states by n. And this is called 0 point energy. This is the difference from classical case, classical simple harmonic oscillator, and the quantum mechanical oscillator. In a quantum mechanical oscillator, there is no state called E is equal to 0. No state called E is equal to 0. The lowest state is E is equal to half h bar omega. This is the difference from your classical case. So the quantum mechanical situation says that the oscillator is never dead. It always has some energy. And this is the 0 point energy. I hope you have understood this. In the next lecture, we will see the wave functions and the Hermite polynomials that come here. I have made the use of Hermite polynomials, but I have not defined. So if you find any difficulty, please do not hesitate to comment. I will resolve the issues, and please watch, like and subscribe the videos. Thank you.